Yeah, 1, 2, 3 at the bottom. All right. So again, hi everyone. And before we start, remember that homework number 1 is due in 2 days, Wednesday. And now, if you haven't started yet, I suggest you at least start soon. And so please prepare a short presentation if you want, of course. This is optional. So next lecture, we're going to start by asking people to present whatever is interesting problems they have solved. So if there is some problem that you're particularly proud of, yeah, short means maybe, I don't know, 8 to 10 minutes, something like this. Or maybe, yeah, not more than 10, but could be less if you want. So yeah, I want to meet everyone and see what they're up to. So yeah, about one homework problem. Hopefully next time we have lots of volunteers who are going to all tell us about, yeah, there's lots of 9 problems in the homework, so probably we'll hear each of them or some subset of them. So any questions on this? All right. So today I'm going to continue talking about regular triangulations. Regular triangulations. And let me remind you what we started doing last time. So today I'm going to switch to point configurations in R to the d minus 1. Previously this was d, now this is d minus 1. Point configuration. Why is it d minus 1? Because it's going to be, throughout the whole class, d, it's going to be more convenient to denote this by d minus 1 for some reason. Now, what I'd like to do is picture should look something like this, maybe. A is something like this. And yeah, I want to find triangulations of A. Triangulations of the convex hull of A, which only use the vertices from the set A. And one way to do this is to choose, or maybe not triangulations, but subdivisions. Choose a function. A function h from A to R. And then I'm going to lift each point of A 1 dimension up. What unique? Well, I mean, it's a function, right? So for each point in A, you get 1 real number. No. Yeah, just any arbitrary function. So then define for each x in A, let x tilde be obtained from x1 all the way up to x d minus 1, comma h of x tilde lives in 1 higher dimensional space, R to the D. And yeah, then P tilde is the convex hull of all these little x tilde points. And now, yeah, so the picture that I drew last time was, A looks, if A looks like this, then maybe I can lift all points like this and get a tetrahedron this, P tilde, or Or I can take the same 4 points here and leave them differently. And there's infinitely many ways I can leave these points. So yeah, now I want to finally let me denote by let pi be the projection from r to the d onto r to the d minus 1, which sends x1 up to xd to x1 up to x d minus 1. Just forget the last coordinate. Back onto the plane. And yeah, now I want to define lower faces of my polytope. I want this polytope to somehow give me triangulations or subdivisions of the convex hull of A. So how do I define a lower face? Okay, so I see. So you want to take a face, project down, and then look at the pre-image, and then you want each point to be minimal, to have the minimal xd coordinate. Yeah, that's a good idea actually. Yeah, I think it works. Yeah, let me give you a different definition. Then in the proof, I'm going to show that these are the same. Yeah, all right, here's a different definition, which is actually, it's pretty convenient to use in practice. So I still want to give that one. So definition, a face f tilde is called a lower face if we have tilde is, remember we had this notation f sub h of p tilde, right, where h is some vector in r to the d, right? So to make this a lower face, I want h where h sub d is strictly less than 0. Yeah, that's my definition, and yeah, but I think it's the same as your condition. So right, is there a face which is, yeah, so you can define upper to make this strictly positive, and question is there a face which is both lower and upper? What do you think? If it's flat. Yeah, if I lifted all my points just to the same plane, right, but if h is the constant function, then the whole polytope is going to be an upper face and a lower face. Okay, any other? Let's say this is not, let's say maybe h is generic in some way. Can this still happen? A single point. So you mean take a vertex, right? If I take this vertex, then oh, my whole polytope could be a single point. Yeah, I mean that's actually a special case of where an h is constant, right? Or well, okay, yes, it's still generic. All right. Oh, yeah. Actually, yeah. It seems like this point actually is both a lower face and an upper face. If h looks something like this, then this point would be an upper face. H this then. So yeah, you can actually get all these lower dimensional faces sort of at the boundary of the projection. You can actually get them as lower and upper. Well, it doesn't have to be parallel to the projection, to this plane here, right? Because maybe even if this edge is slightly tilted, you can still choose h to be perpendicular. So let's take this face here. Right? Let's assume it's not parallel to the plane. Then to get an h, correspond to this edge, I would need it to be perpendicular. So there's like a one-dimensional space of h's which give me this, and some of them are going to be upper, some of them are going to be lower. No, actually, well, not every face, right? So this top-dimensional face here. Well, okay. So for this is a two-dimensional face, right? So the only h that works would look something like this, and this has positive these coordinates. Well, actually, still no, because this vertex here is also not a lower face. And that corresponds to the other definitions. So that if you project, right, there's this whole line segment inside my polytope, which as you project, only the lowest point from each pre-image of a point is going to belong to a lower face. All right. Theorem. Let A be a point configuration inside R to D minus 1. Then I want to take C sub H. H is some function from A R. Then I'm going to define C sub H to be the set of all phi of F tilde, where F tilde is a lower face of P tilde. This collection of polytopes is a subdivision of A. And in particular, if H is generic, then C sub H is a triangulation of A. And what is generic in this case? What do I mean by generic? And it's actually category 1. Okay. Yeah, still unclear. Okay. Yeah. I find what? Of what? I see. So you want the lifted point to be affinely independent. You want any? Okay. Yeah, up to a certain number of points. Yeah, that's actually that actually works. So any D points in A tilde are affinely independent. Well, are finally span R to the D. That's good. All right. So how do I prove this? I'm actually, yeah, before I even prove this, let me try to give you some examples. Because this, yeah, by the way, so definition, such subdivisions or triangulations which can be obtained in this way from some H are called regular. Sometimes they're also called coherent, but we're going to use regular. I think it's more widely used. So examples. Give me an example of a regular triangulation. A triangle. This is regular. Okay. What is my point configuration here? Three vertices. Okay, let's say, so I'm going to note in red my A. So A is these three vertices. Okay, that works. Yeah, give me two-dimensional examples, let's say. A triangle and a point inside. Okay, so if A is a triangle is a with a point inside, then what would be a triangulation? What would be a regular triangulation? Or yeah, or you can still have the four vertices, but you're not going to use the middle one, right? And then still use only the whole triangle. So these are the two pictures we get from there. All right. If let's say if A is a set of vertices of some convex polygon, then let's say I take. Seems like all triangulations should be regular. Actually, interesting. Is that true or false? Is it true that if A is vertices of a polygon, is it true that any triangulation of a polygon is regular? Nice. Okay. So indeed, this is true. So any triangulation is regular. And proof, indeed, origami fold just a bit. So for now, just for polygons. But that's actually a good question, right? So, all right, is it true that any triangulation is regular? Or is there an example of a non-regular triangulation? You take endpoints in the plane like this, then even any subdivision of such a polygon is regular. Could it be that some triangulations somehow cannot be obtained from choosing any h? Yeah. An example of a cube. Okay, so you want to draw a three-dimensional cube. Okay, so you wanted to draw a tetrahedron here, and a tetrahedron here, right? Oh, so you want some triangulation which doesn't fit together as we had previously in the example, right? Or see? I mean, so the triangulation we had where there was, so remember there was one pyramid and another pyramid, and then we had two different ways of these faces fitting together. That is not a triangulation. So in my terms, right, triangulation has to satisfy this extra condition that the intersection of any two simplices is their common face. So actually, yeah, this. Okay. Yeah, that's a good question. So and we have to use our 4D imagination, right? If they do stick together like this, is it regular or not? And it's actually, yeah, this is pretty, I don't know actually off the top of my head, probably regular. Yeah, this is probably regular. A skewed octahedron. What is a skewed octahedron? But I mean, if I fit, so this, if I remove these two simplices, then I get an octahedron, right? And then it doesn't have this many triangulations. It's like, I mean, there's this triangulation, there's the one where you, or I mean, I think all triangulations of the octahedron are obtained from this one by symmetry. So yeah, and I think all of them, at least one of them has to be regular. So all of them I think are regular. Yeah, actually, three-dimensional examples is too much because I mean, yeah, you have to project four-dimensional polytopes onto the three-dimensional space, and it's hard. Hard. Yeah. So instead, yeah, this actually it's actually not so easy to come up with examples of non-regular triangulations. It looks like all triangulations you see in real life are regular. Here's an example of a non-regular triangulation, which is I want to take 6 points in the plane. I want them to look like this. The triangle inside another triangle. And triangle, triangle. And yeah, and then I want to choose the triangulation. So claim this triangulation here. So A, again, A is 6 points. This triangulation here, claim this is not a regular triangulation. And you can, it's a nice exercise. But yeah, some triangulations are non-regular. And then you can ask, well, what if A is in convex position, right? What if A is the vertex of a polytope, and still, like in higher dimensions, you still get non-regular triangulations of polytopes. So, and in fact, I think the majority of triangulations, asymptotically, like almost any triangulation is going to be non-regular. Any questions so far? All right, so let me give you a proof. I want to prove the theorem that was on this blackboard. Right, that, oh, actually, that's the theorem. I get that. I want to prove that that collection of polytopes is a subdivision of A. So how do I do this? I need to check. Maybe I should remind you with the definition of a subdivision. There was 3 conditions. Does anybody remember the 3 conditions? Each vertex, oh yeah, that's actually the 4th condition. Vertices of C should be a subset of the vertices of A. Yeah. Okay, the union of all faces in C. Was that the 3rd? I didn't actually. It's the convex hull of A. And it should be. Oh, it should be subdivision of A. All right. Yeah. Okay. Intersection of any 2 faces is a common face. face of both of them. All right. All faces of the original polytope, and moreover, all faces of each polytope in the subdivision are right. There was actually we never had this condition that the faces of the original polytope should be, because A could have a point on the boundary of my polytope, and I would be allowed to use. And yeah, so any faces of any f in C belong to C. All right, so which of these is easy? Which of these we know immediately? Four. Oh, interesting. We know 4 immediately. Why is that? Obvious. Okay. Yeah, okay. Yeah, all vertices of my P tilde are obtained by listing the points in A, so when you project, the vertices go to vertices. Yeah, okay, obvious. All right, now let me try to prove the rest. I want to prove 1, so I need to take a face of P tilde. I need to take a lower face of P tilde. Let F tilde be the lower face of P tilde. And then, so maybe F tilde is F sub H of P tilde, where H sub D is negative. Yeah, that's actually a good question. Let me, because I mean, I want to prove subdivisions result in general. So I'm not assuming H is generic. Just, I mean, I can, by definition of the a lower face, it is a face of this form where H sub D is less than 0. Oh, I mean, this, wait, why is it? Which one on the right? Okay, so here, wait, did I write subset? Vertices of C subset. Yeah, okay. Yeah, thanks. All right, so I have my polytope P tilde. And then I have maybe this thing here is my face F tilde. And then maybe my H looks like this. So I want to show that if there is a face G tilde, so let's say let G tilde be a face of F tilde. And I want to show that G tilde is also a lower face, because that would be enough to show that there's no right. So I want to show that G tilde is a lower face than G tilde is a lower face of P tilde. Why would that be true? Oh, I see. So you wanna use the projection property. Yeah, maybe I should prove the projection property. I was actually I should just prove the let's prove the projection property. That's even better. Let's do this. So yeah, let's even forget about this for now. I'm gonna even go to a different blackboard. So suppose that x be inside the convex hull of A, then the preimage of x is a line segment. Is of the form x tilde and x tilde prime, where, let's say, x tilde sub d is less than x tilde prime sub d. Then I want to claim, yeah, well, okay, less than or equal to. So if they're equal, then it's fine. So let me actually assume, well, okay, then the claim is that x tilde double prime inside this interval belongs to a lower phase if and only if x tilde double prime is equal to x tilde. Right? So in each preimage, only the lowest point belongs to the set of lower phases. Okay, this is the claim. How do I prove this claim? Suppose that maybe suppose that x tilde double prime belongs to f sub h of p tilde, where hd is negative. Then what do I do? All right, so indeed, if I take decrease, well, all right, so indeed, if I take the inner product of h with x tilde, let's say, then, well, x tilde is obtained from x by lifting with one extra coordinate. So it's the same as h1 up to hd minus 1, the dot product with x plus hd times x tilde 3. So, and the same is true for if you put any point in the preimage of x. So in particular, because this thing is negative, so x tilde belongs to fh of p tilde if and only if this has to be maximal. So x tilde d has to be minimal in the preimage. If and only if x tilde d is equal to, well, x tilde double prime is equal to x tilde d, if and only if x tilde double prime is equal to x tilde. I guess that's the whole proof. All right. So now going back to this proof, indeed, this becomes obvious, because if the closure of f is, if all points satisfy this property, then any point in the closure of f is going to satisfy this property. All right. Done by the preimage property. All right. What about 2? Intersection of any two faces is their common face. Say f tilde and tilde prime, two lower faces. Then y is, well, what I actually want to show is, because this subdivision is obtained by projecting down. We want to show that the projection, the intersection of the corresponding two faces downstairs is a common face of phi of f tilde and phi of f tilde prime. Yeah? Okay, so but that's good. So we know that f tilde intersect f tilde prime is a common phase of f tilde and f tilde prime. Yeah, that's a good idea. So upstairs we know everything is good. But what happens if I project? In general, it's not the same as like the intersection of any. It's not true in general that if you project this intersection, then you're going to get this intersection. So what do we do? Oh, so you're saying that this intersection should be equal to the projection of this. Oh, interesting. I see. Okay, so you're saying the union of lower faces projects bijectively onto the convex hull of A. All right, yeah, that's actually true. So phi of tilde intersect tilde prime is phi of f tilde intersect phi of f tilde by this property here. Yeah, okay. So we're done with 1 and 2 and 4. I guess 3 is, and actually also 3. Basically, 3 also follows from this property as well. Because you take any point in P and then you lift it up to such a line segment. You take the lowest point of this line segment, then that point is going to belong to a lower face. So actually, we're done with all 4 properties. Any questions on the proof? No questions? All right. So now I want to discuss flips, which I think is a very interesting subject. I like it a lot. So what is a flip? Let's assume, for simplicity, assume that your point configuration A is that RD minus 1 is in general position, which means that any D points finally span the whole R to the D. So, and let me denote, so let's say I have n points. N is just the number of points. And I want to consider some special cases. So let's say I have and let's say assume that n is at least greater or equal to D. Because I want the whole of A to span the whole of R to D minus 1. So what happens if n is equal to D? The convex hull is a simplex. Nice. Convex hull of A is a simplex. D is D minus 1 dimensional simplex. All right, so this is uninteresting. There's only one triangulation. Because the simplex is already alpha simplex, so there is only one triangulation there. Right. Okay, so what about n equals to D plus 1? if n is equal to d plus 1. So for example, let's see, I have maybe 3 points on a line. Or, yeah, so for example, I have 3 points on the line. That's allowed. N equals to 3 and d equals to 2. Or I can take n equals to 4 and d equals to 3 and get 4 points in the plane, something like this. So what happens in these cases? Yeah. There's 3 triangulations. There's 2 triangulations. All right, so indeed, if you have 1, 2, 3, then you either get the whole line segment as a single simplex, or you get 2 simplices. And what about n equals 4 and d equals to 3? Also 2 triangulation. All right. So here you can have this or this, and also, well, there are sort of 2 different options for A. If A looks like this, then you also get 2 triangulations. All right. Is that true in general, that you always get exactly 2 triangulations for this case? Okay, interesting. So you're saying I'm giving you all right. Yeah, and indeed, actually, I am giving you clues. And even actually, I think last lecture, I even told you that this is always going to be true. So, and let me actually prove it. So I have 7 minutes. All right. So let's say A is a bunch of points, A1 up to A d plus 1. And, in that situation, I'm actually going to say, so yeah, let me make a definition here. So I see, with all of these assumptions, right, points have to be in general position, and n is equal to d plus 1. Then I'm going to, by definition, I'm going to say that A is a circuit. By a circuit, I mean a minimal set of points which are affine dependent. Minimal, finally dependent set of points. Okay, so if this is a circuit, then there is an affine dependence between them. So how does an affine? There should be an affine relation, dependence between these points, and it should be, it's of the form sum of Ci AI is equal to 0. I comes from 1 up to d plus 1. And I can take these points with some coefficients, not all, well, actually, all Ci are not equal to 0. Right? Because if some Ci is equal to 0, then this will not be a minimal affinely dependent configuration. Okay, so now let's say I want to look at regular triangulations. Let's H from A to R is generic. Then what I want to do is I want to look at the sum of Ci H of AI. So this is a unique affine dependence between these points AI. So what I want to do is I want to lift flip these points to higher dimensions and see what happens to the last coordinate, the resulting tilde points. And if H is generic, so by definition, here H is generic if and only if this is not equal to 0. Yeah. AI minus A1. Well, actually, well, okay. I mean, certainly if they are fine independent, then this should be true. Yeah, but you're right. You're right. The sum of the CI should be equal to 1. Maybe I should write it down. Yeah. So, but my point is that, so if you look at this number here, it's if it's 0, then the corresponding subdivision is going to be the whole, just the convex hull of A. But if it's either positive or negative, you get 2 different regular triangulations. If depending on whether this sum is positive or negative, you get 2 different triangulations. The sum of CI should, oh, you're saying should be 0. Okay, maybe it should be 0. Wait, why would it be? Yeah, I think it should be 1. Yeah. Yeah, because, or maybe 0. Yeah, anyways, never mind. So, anyways, so first of all, here's an exercise. Prove that these are the only 2 triangulations. There's no more. All triangulations of a circuit are always regular. So that's one claim. And now, yeah, the definition in general is that if A is an arbitrary point configuration satisfying those conditions, if A in R to the d minus 1 in general position, then a flip of a triangulation C consists of replacing one triangulation of a circuit with the other one. Right? So maybe I take A to be 5 points like this. Right? So then I can look at all possible triangulations of A. And there's many triangulations. There's a triangulation that looks like this. And then I can apply a flip to it. And maybe I could even put it here. If I apply a flip, I can actually do it in 2 different ways. I can flip my configuration like this, or I can flip it. What's the other way? Flip this triangulation. I can add the strange point to wait, what? All right, and then now I can flip this triangulation again, so maybe I get something like this. I can't flip all circuits. Right, that's true. So given a particular triangulation, there's only a few moves which are available to me, not all possible circuits. And you can keep going. And of course, Of course, if A is just the vertices of a convex n-gon, you get the associahedron. The graph of triangulations is going to be the one skeleton, the associahedron. But in general, you can take a bunch of points and try to look at all triangulations and see, there's all sorts of questions. So yeah, I'm going to continue next time. I'm out of time. See you all on Wednesday.